Hello, everybody. It's a pleasure to be here. I have a confession. I used to work in the security industry before I went over to the dark side and became an academic. And when I was in the industry, one challenge that I saw was that customers were wanting to know not just the list of attacks and vulnerabilities and exploits that the product could prevent, but they were also asking how much money is this going to save me? So today, I want to share some ideas about this. These ideas are perhaps a little bit controversial. That's because we just recently started understanding the science behind making these predictions in security. But I'm really interested in how you think about these issues. So I would like to start with a thought experiment. So I would like you to think of one time when you had to give security advice to a non-technical person. I have a show of hands who can think of such a time. You know, maybe it was a family member, customer, a boss. OK, fair number of people. OK, so now how do you do it? Do you try to scare them? Do you try to tell them about all the bad things that can happen if they don't become more secure? Okay. All right. OK, and then did it work? Did they take your advice? Can I see very few hands? OK. Yeah, so it does seem to be hard. People seem to be thinking about this a lot. What is the benefit of security? How much money am I going to save? And sometimes they estimate, their estimations are a little bit off. For example, CV-2017-0144 was a vulnerability in Microsoft Windows in the SMB component. This vulnerability was publicly disclosed in March 2017. And at the time, Microsoft also released a patch for this vulnerability. And later that year, this vulnerability was exploited by the WannaCry worm, which very quickly spread around the world, and the NotPetya worm, which managed to infect multinational companies, such as the Maersk Group, which is a shipping corporation. It shut down the company's networks, which forced them to keep 76 ports closed for 3 days. And the company estimated that this resulted in $300 million loss for them. So, and these are exploits of a vulnerability for which a patch was available. Okay? So why is it so hard for our community to convince people to stop putting themselves at risk? So let's take a look at this from their perspective, perhaps. So let's step in the shoes of a business executive who tries to decide whether to patch all the vulnerabilities in their infrastructure. Now, business people tend to think about these things in terms of cost-benefit trade-offs. So the cost to patch all the vulnerable systems, they can probably estimate it fairly accurately. Now, the benefit, of course, is hedging the risk that one of these vulnerabilities is going to be exploited and they are going to get hacked. So the risk is the probability multiplied by the impact. So there's two terms here. So we have to estimate each one of them. So for the impact, we can look at comparables. So fortunately, or probably unfortunately, we have a lot of data to look at similar losses. So maybe we can estimate this one. But what about the probability? Today, these probabilities are estimated by asking subject matter experts. So usually, the risk, the probability is derived from an expert's opinion. So in other words, while the cost is reflected with an objective metric, the risk, the benefit is expressed in subjective terms. And today I'm talking about vulnerabilities, but this is a broader challenge for the security industry. Many security products, the customers have to compare the objective cost of those products with benefits that are expressed in these subjective terms. And I think we can do better as a community. So today, I will tell you what we have learned after 5 years of research and analyzing data from 10 million hosts about this problem. I will share 3 ideas for predicting exploitation in a data-driven fashion. And first of all, the first question to ask is is this even possible? Can we predict exploits at all? Is this a problem that we can learn about, we can gradually get better at doing it, or is it more like predicting stock market crashes? And to do this, we have to figure out a way to validate our predictions. And we should validate them using real-world events, real-world incidents, exploits that are actually used and active in the wild. That's because we already have risk metrics, vulnerability metrics, such as the CVSS score that is attached to each vulnerability in the National Vulnerability Database. It is, in fact, recommended by the NIST for prioritizing response to vulnerability disclosures, but it is prescriptive. It is not validated against real-world incidents. So to do this, when I was at Symantec, I built an infrastructure called the Worldwide Intelligence Network Environment, or WINE. This was a data analytics system that combined data from hosts around the world, from about 10 million hosts. And for example, we could see if certain IPS or antivirus signatures were triggered on those hosts, that indicated that a specific exploit was attempted. So in this way, we could tell which vulnerabilities are exploited in the wild. All right, so let me tell you the first idea, and the first idea is to use machine learning, okay? We use machine learning broadly in security for a variety of purposes. And machine learning, in a nutshell, it learns from examples. So it starts from a few known examples of vulnerabilities that are known to be exploited and known not to be exploited. And then it tries to learn a model of what an exploited vulnerability looks like. And then it tries to compare the remaining cases, the remaining vulnerabilities to these examples in order to classify them in these 2 classes. And whenever using machine learning for such a problem, we have to ask 2 important questions. The first question is, what features of vulnerabilities are we using to compare them? And then the second question is, if the prediction works, did we get lucky? Or does this actually capture some meaningful mechanism? Do we understand why the prediction works? So perhaps the most straightforward way to use machine learning would be to look into intrinsic vulnerability features, such as the CVSS score, the category of the vulnerability, the various references that are included in the National Vulnerability Database. And indeed, the earliest system that tried to predict exploitation used these intrinsic features. So they trained a linear SVM classifier, and they reported 90% accuracy. The best feature that they had was whether a vulnerability had a bug track ID. The weight for this in their classifier was twice as high as the next best feature. Okay? But they predicted the existence of proof of concept exploits because they used information from databases such as ExploitDB to label their vulnerabilities as exploited or not exploited. Now, when we tried to repeat this 5 years later, we could still achieve a fairly high precision and recall for proof of concept exploits. However, when we tried to predict exploitation in the wild, the precision of our classifier did not exceed 20%. And the precision is the ratio of correct predictions, the number of correct predictions, to the total number of exploit predictions that our classifier makes. So this means that most of our predictions are false positives. And to understand this, we have to take a step back and try to understand a little bit better what we are predicting in this way. Because the risk of exploitation depends on the vulnerability, of course, but it also depends on the attacker's capabilities and on the user behavior. So intrinsic features just capture the first aspect. So it is very hard to get good performance, good prediction performance with just intrinsic features. It's in some sense like trying to sell car insurance by taking into account just the properties of the car and not looking at all at the environment or the driver's habits. But I want to emphasize that the problem here is with the features that we chose, not with using machine learning itself. Machine learning actually, the utility of machine learning was in discovering good predictors, such as the bug trap thing. OK, so now let's try to capture the other two components, the attacker and the user. So our second idea is to look at the dissemination of information about vulnerabilities and exploits among hackers. To give you an intuition for why this might be useful, I want to go back to this exploit that was used by WannaCry and NotPetya. This was a weaponized exploit called Eternal Blue, allegedly developed by the NSA, that was leaked online. And this was widely discussed 1 month before, 1 month before the attack. So it was discussed online, on social media. And at the time, this should have indicated that this particular vulnerability carried a higher risk of being exploited than other similar vulnerabilities in Microsoft Windows. All right, so let's try to plug into this discourse. And let's use Twitter. In 2015, we built a system that, again, uses machine learning. So we used the CVSS features and other intrinsic features as in the prior work. But in addition, we also looked at Twitter. We extracted specific words that are used in the security discourse, as well as features that indicated how popular these topics are. We tried to predict exploits in the wild, and we trained a classifier, also a linear SVN classifier. And one thing we observed is that for about 80% of the vulnerabilities that were exploited in our data, there were some tweets before the exploit was discovered. Right? So this indicates that in 80%, there was an opportunity for making an early prediction. And the system allowed us to double the precision compared to just intrinsic features. But I want to go back to this question. Did we get lucky? Do we understand why this works? And it is useful to look at the contribution of each feature to the prediction. So the intrinsic features, as I mentioned before, they have a high recall, meaning that they catch vulnerabilities that are actually exploited. But their precision is not very high. So they have many false positives. So now, interestingly, the Twitter-based features, which indicate how information spreads, have the opposite effect. They have a high precision and low recall. So this suggests to us that we actually need both. They have complementary effects. And in order to get better at predicting, we have to look at both. And the reason for this is that there are constraints on adversaries, on real-world adversaries. Creating weaponized exploits is hard. So they look at these things that are published online. And there are things that are posted on social media, like Twitter. And we can plug into this discourse in order to extract useful signals for prediction. OK, so that's the attacker side. What about the user side? And we have to understand a little bit how to use the factors of cyber hygiene for predicting. And of course, here we're talking about vulnerability exploits. So the cyber hygiene corresponds to patching. So in 2015, we conducted, again using Wine, we measured patching of nearly 1,600 vulnerabilities. And over 5 years, we measured the vulnerable population to each of these exploits, and we did this every day. So we tracked how this population goes down every day as these vulnerabilities get patched in the wild. And while generally patching starts quickly for most vulnerabilities, reaching 50%, a patching level of 50%, so patching half of the vulnerable hosts, that is a much slower process. It is a long-tail distribution, and we're seeing many hundreds of days in order to reach this level. So this suggests that there are differences, important differences across hosts in the speed of patching. And we also saw differences across vulnerabilities and even across different patches for the same vulnerability. On this plot, I'm showing one vulnerability that affected both Flash and Acrobat Reader. And the two patches had very different propagation patterns. In particular, the Flash update they started about the same time, but the Flash update never actually was much slower and never actually reached the 50% mark. And as a result, this vulnerability was used in about 30% of the spear phishing attacks in 2011. So we have seen high variability of patching delays across hosts and across vulnerabilities. So now let's try to use this as a predictive factor. And to explain how this works, I'm going to use an analogy. So think of a physical virus, a biological virus that spreads using a mechanism that is not yet known. One thing we could do in this situation, we could look at the infection symptoms. We could cluster them. And then within these clusters, we could look at the distribution of different risk factors. So for example, if we see that the exposure to air contamination is about the same inside the infected cluster and the uninfected cluster, but the exposure to water contamination occurs mainly within the infected cluster, then we can infer statistically that this virus probably is probably waterborne. So now let's bring this back to the cyber realm. In place of the infection symptoms, we could look at signals such as the number of IP addresses that are blacklisted. And we can see that there are ISPs that have very similar trends in how their hosts are blacklisted over time. So we clustered them. And then our risk factors here, of course, are the patching delays for various vulnerabilities. So we are going to compare them inside each cluster and across the whole population. And in some cases, we don't see a big difference. But in other cases, we do see a big difference. And indeed, it turns out that in the cases where there is a big difference, these vulnerabilities are really exploited in the wild. So based on this idea, we built another, just last year, we built another machine learning system. In this case, we were able to predict exploitation in the wild with 10% false positives and 10% false negatives after observing only 10 days of historical patching. And we played with a number of features. This is what this chart shows here. But the symptom risk features, the features derived from the symptom risk similarity and the intrinsic features accounted for most of the performance of this classifier. And the reason why this works is because patching patterns indicate the targets of opportunities for attackers. I would like to end with a call to action. So the first thing I want to make sure is that my message here is not that we should use these models, these predictive models, to patch vulnerabilities selectively. Of course, we should try to patch all the vulnerabilities and to adopt additional security measures for defense in depth. However, when users ask us, what are the biggest risks for me, for my systems, then we should give them risk profiles that are validated using real data. So here are a few pointers. If you go to this link, you can see a demo. We made available a demo of our Twitter-based predictor. Some of these ideas have started to be commercialized. So last year at RSA, I saw there was a talk on predicting vulnerability exploitation that described an actual service that is offered by a company called Kenna Security. And they use the first idea that I mentioned today, so prediction based on intrinsic features. And on Monday, we had a very interesting roundtable here at Enigma, where a lot of other interesting ideas were discussed as well. But I don't want to just say what we can do today. I also want to say a few words about what you can do tomorrow. And when I advise companies on cyber risk, I like to point out that over the past 10 years, there has been a lot of research, a lot of advances on how to make these predictions, not just on which vulnerabilities are going to be exploited, but also on which websites are going to be hacked, which data breaches are likely to occur, when users are likely to be exposed to malicious content. So there is an opportunity to start incorporating some of these ideas in tomorrow's products and services in order to better convey to users what is the benefit of security. So I would like to leave you with two thoughts. Taking a step back from all the technical details, my first thought is that predictive models for security are increasingly based on rigorous science, and that they measure risk objectively by using data rather than subjective opinions. Thank you.